Welcome back, Year 11. This is the 9th and final lesson of radioactivity. It's a lesson where you're not going to be learning any more content, but reinforcing what you should have learned so far, and in the context of past paper GCSE questions. So please put lesson 9 and date at the top, and the title is exam questions. Question 1 is a self-assessment question where I'd like you to have a go at 1A, 1B, and I've just put a little hint there for the very last part of question 1. It says copy the graph and sketch a decay curve for a radioactive substance, etc. So I'd like you to use the sketch above here in order to complete that. So press pause and then press play again when you completed question 1. So let's take a look at question 1. It asks, select the statements below. So statements, that's plural, and the other giveaway, look, there's 2 marks. So statements, not statement. Meaning of half-life of a radioactive substance. The time taken for the radioactivity to halve. I'm not sure about that one. Time taken for the atoms to split in half. No, they don't split in half, they decay. The time taken of the number of undecayed particles to halve. That sounds as if that could be one of them. The time taken of the count rate to halve. Certainly it would be that. You'd hope that it would have from the original value. And the time taken for half the alpha particles to decay. You know, you don't know if they're going to be alpha particles, and it's not the alpha particles themselves that decay. The alpha particles are emitted, so it's certainly not E. It's certainly not B. And if we look then at C and A, time taken for the radioactivity to halve, how do you measure radioactivity? You don't really, you measure the count rate. So let's look at C again, the time taken for the number of undecayed particles to halve. Yeah, that would be right. So the correct answer therefore is C, C and D. Turn on to page 61, please. Shows a decay curve. Part 1's asking to use the information to write down the count rate after 100 days. You can probably see by just looking at the graph. Useful if you use a ruler as well. You go up from 100, you go across, and you can see the answer there is 400 counts per minute. Just write down here the answer. That's going to be 400 counts per minute. Right, so part 2. Write down the half-life of this radioactive substance. Well, remember, the half-life is the time taken for the count rate to drop from its original value to half its original value. So half of 800 is 400. We work at the time, which is going from here, 0, up to, well, we've just seen actually using the ruler. If you go across from 400, you come down, and that's at 100. So that's going to be 100 days. Part 3. Write down the time it would take the count rate to fall from 50 to 25 count per minute. Well, because it's going from 50 to 25, again it's halving. So the half-life at any value is 100 days. Let's say though you were in the exam and you still weren't sure. Let me just write down the answer there, 100 days. Excuse me. I think you'd probably struggle finding 50 on here. Let's just do, that's 100, that's 50. Yeah, you wouldn't be able to do it from the graph, so you just have to know that. And the final part then, I'll copy the graph and sketch a decay curve for a radioactive substance that has a starting count rate of 800 counts per minute, with a shorter half-life. Now, a shorter half-life means that it would go from 800 to 400 in less time. Let's look at the graph. Now, when you do this, let's go from a half-life of 100 to a half-life of, let's go for 25 here. That means that the time it takes to go from 400 to 200 is also 25. So every 25 days it's halving. So the graph would look something like this. I'll just use a different colour to draw that in. So, in fact, any curve underneath the existing curve would be fine. Just move that ruler out of the way. So you don't need to do as I just did there. I wanted to just make the point that a shorter half-life would be anywhere underneath this curve. So, question 2, another self-assessment. Make sure, please, that you mark them right if they're right, or correct them if they're wrong with a red pen, as you should always be doing with self-assessment questions. Question 2, mass of a sample of radioactive isotope 64 grams, and it has a count rate of 800 counts per minute. Always good practice, remember, to highlight the important parts. It's a gamma emitter, that might become useful, and half-life of 30 minutes. Find out how many half-lives it takes for the count rate to fall to 50 counts per minute. Well, again, what I'd like you to do is pause the video, and part B is an explain, which you'll do underneath here. And when you've completed, press play. Right, so part A, find out how many half-lives it would take for the count rate to fall to 50. We're starting off with the original count rate of 800, so there's a little bit of a helping hand there. If you put 800 there, after one half-life, it falls to 400. I think the idea is you put the values in there. After another half-life, drops to 200. Another 100, and another will drop to 50. So if we count the number of half-lives, there's 1 there, that'll be 2, that'll be 3, and that'll be 4. So how many half-lives would it take? It's 4 half-lives. How long does it take for the count rate to fall to 50 counts per minute? 50 counts per minute. Well, to do that, you'd have to multiply, and I'll do that part actually underneath here. So the time taken, you'd multiply the number of half-lives, number of half-lives by the time of one half-life. Half-lives. You don't actually need to write out this equation. It's not an equation that you'll be given, it's just applying a bit of numeracy. Time for one half-life. So we know we've got 4 half-lives. We know one half-life is 30 minutes. Four times 30 is 120 minutes, which equals 2 hours. Part 3. What mass of the radioactive isotope remains at this time? Well, it's the same idea as the count rate dropping. So we could do the same thing here. We'd start off with 64 grams. I'll just use a different colour. 64 grams to start off. Drops to 32 grams after one half-life. 16 grams after 2. 8 grams after 3. And then 4 grams after 4. Okay, so 4 grams would remain. And then part B, explain why this radioactive isotope would be suitable as a tracer in medicine. What you need for a tracer in medicine is a short half-life, 30 minutes, and a gamma emitter so that it can be measured outside the body. Alpha and beta wouldn't move from inside the body outside the body, wouldn't penetrate through. So let's just write down that explanation, part B. I'm not going to write it down, I'll just put down the key words. Short half-life and gamma emitter. And in your explanation there, you say why you need a short half-life. So you need a short half-life so it doesn't stay in the body any longer than is required, and a gamma emitter so that it can be measured outside the body. Question 3, teacher assessment. So I'd like you to do that. I'm not going to give you the answers for that, so you just complete question 3 then on page 62, and the same please for question 4. When you've completed, obviously press play. Moving on now then to page 63, higher tier questions. The first, so we've got 1, 2, 3 pages, 4 pages, and we've got question 7 there will be a teacher assessment, and the rest will be self-assessment questions. Let's look at question 4, a bit to read, so I'm not going to read it all out. You do it, same again. When you've completed, press play and I'll go through it with you. Okay, so part A, state what is meant by the following statements. Carbon-14 is a beta emitter. Again, I'll give you I'll speak the answer and you check against your answer. Carbon-14 is a beta emitter. That means when carbon-14 decays, it emits a beta particle, which is a fast moving electron. Part 2, carbon-14 has a half-life of 5,720 years. This means that every 5,720 years, the count rate decreases by half. You could also have said that the number of undecayed radioactive atoms decays by half. Part B, copy and complete the decay equation for carbon-14. So rather than copy and complete, I'll write the answers here. So carbon-14 decays to nitrogen. Now, knowing that a beta particle is negatively charged, it's got a mass number or nuclear number of 0, will help you complete this, because the numbers on the bottom of both sides of the arrow have to be equal. So 7 minus 1 is 6. And at the top, 14 equals 14 plus 0. So you can see what's happened there. One of the neutrons in the carbon atom has changed to a proton, and a beta particle has been emitted. Moving on now to part C. A bone taken from a skeleton found at a site contains 10 units of carbon-14. Identical bone in a living animal has 160 units. Use your understanding of half-life to calculate the age of the skeleton. So do some workings underneath here. C, part 1. So what's happening is, every half-life, the units, they use units, it could be mass, it could be count rate, doesn't matter. We keep doing this, halving it until it gets to 10. Now how many half-lives have we got? 1, 2, 3, 4 half-lives. The age is going to be 4 half-lives times the time for 1 half-life, which is given to you above, 5,720. Just using a calculator then, multiply 5,720 by 4, that's giving you 22,880. And the units, years. See, part 2, explain why this method of calculating the age of bones is unreliable for skeletons believed to be less than 100 years old. Well, the answer there really is that it's difficult to measure accurately the small change in activity that would occur in only 100 years. Turn now then please to page 64, and on page 64 I'd like you to do question 5, and press pause then. When you completed question 5, press play. On to question 5, a self-assessment question again, so just read and answer in the space below. Pause video now and play when complete. Okay, this time I've written the answers below, so I'm going to talk you through the answers and just highlight as I'm going along. First question, what's an alpha particle? That's straightforward. An alpha particle is a helium nucleus. Remember, that's equal to 2 protons and 2 neutrons. So a helium nucleus is like a helium atom with all the electrons removed. Question 2, explain why the detector would not work if the radioactive source emitted gamma rays only. Well, gamma rays would not be affected by the smoke. They would penetrate through the smoke. So if in the event of a fire, smoke would be produced, but it wouldn't affect the amount of gamma rays reaching the sensor, so the alarm wouldn't be sounded. So it would basically render the smoke alarm useless. Question 3. Explain why, in normal use, the radioactive source in the detector is not a risk to human health. Remember, alpha sources are not dangerous outside the body because they can't penetrate through the skin and affect cells in the body. And also there's a casing around the smoke alarm which the alpha particles can't penetrate through. So the answer to question 3, look, the alpha source in the detector is not a risk to human health because, here's the answer, the casing of the alarm acts as a shield and alpha cannot penetrate further than a few centimetres of air. B. Part 1. Why is americium more suitable than curium? Well, it's because curium's got a shorter half-life of 160 days compared to americium, so the smoke alarm would last longer using americium. So safe to use for many more years. I'll put the full answer there. The unit of activity is the becquerel. That's the shortened normal way in which we'd write it down, or that's the full word. Remember, that was named after the scientist Henri Becquerel. B, part 3. Let's have a look. Calculate how long it would take for the activity to drop to 26,000 units, and the original activity is 52,000. Well, 26 is half of 52, so that's going to be one half-life, which is 432 years. And part 4, the final part of part B, calculate the mass of americium remaining after 864 years. Well, remember that the half-life is 432 years, so 864 years is twice 432, so that's 2 half-lives. Therefore, the mass would reduce twice, once, twice, and remember the units, micrograms. Turn it on to the next page then, please. Question 6. Again, this is a self-assessment, so what I'd want you to do is to answer this, and when you've completed it, press play. So press pause now, please. Part A, explain what is meant by the half-life of a radioactive substance. Just written it down there. Half-life of a radioactive substance is the time taken for it. So at this point you could have written in, doesn't need to be its activity, you could have said the number of undecayed atoms to drop to half their original value, the count rate to drop to its original value. I've written down its activity to drop to its original value. B, when a Geiger counter was left out in the lab, it showed a count rate of 20 counts per minute. What's the cause of that? That's background radiation. B, part 2, the Geiger counter was then placed in front of a beta emitting source, so I'm just highlighting that. There's the beta emitting source, there's the Geiger counter. When the source was taken away, the Geiger counter still showed 20 counts per minute. Use a graph to complete the table below for the count rate that would have been produced by the source alone. What you need to understand here is that the readings shown on the graph are partially due to the beta source, but partially due to the background radiation. So if we look at time 0, if I show on the graph here, up to 80 would be due to the beta source, but then going from 80 up to 100 is an extra 20, is due to the background radiation. So we've got to take 20 away from each of these values. Just be careful you don't get caught out here. It's not going up in 5, it's going up 5 and then jump 10 and a jump of, what's that, 5 again and 5. So you've got to check each time. So we'll do 5 first of all. Look where 5 is on the graph. Just use a ruler to make it more obvious. There's 5. So we're looking on the graph now. Find out the value and take 20 away. So just change the pen. That's 82. That's 84. That's 86. It's between 86 and 88, I would say there. So we'll call that 87. We then got to take 20 away. 87, take away 20, gives us 67. So we put 67 down in the table. I'll do one more with you. 15. So find 15. Get the ruler. And if we look at the scale, between 60 and 80, that's 60, that's 80, we're going up in 2s. So 60, 62, 64, 66, 68. 68, take away 20, the background radiation gives us 48. Again, write that down in the table. So you should have done the same for the others. I'll go ahead and do that now. Now, in an exam, there'd be a level of tolerance in terms of getting a mark right. So I'd allow 2 marks either side. So if the first one there, anything between 65 and 69. Next one here between 46 and 50. Quite a generous level of tolerance there. Perhaps it'll just be 1 mark or one count rate either side, but we'll do that. We'll give you that tolerance because sometimes when you photocopy graph paper, it's not so easy to get that level of accuracy when you read it. So when you've completed the table, part C, use your results from the table, draw the activity graph of the source alone. Use a graph to the left to complete this. What you're doing then, you're using these values, I highlight in here, to plot a new graph underneath. The first one then at 0 time would be 80. I'll use a different pen, perhaps, let's have a look, it's green pen, yeah, green. First one there is 80, and then you take the other values. So my next one is 67. Find 67. 2, 4, 6, 7. I'll go ahead and complete. Okay, I've plotted my points in green there. I'm just turning my screen around because, as I've explained before, it's good to move the screen or your booklet around to get an easier way, I should say, of drawing in that curve of best fit. And it's a curve of best fit. Remember, it doesn't need to go through each point exactly. So that's part C. Part D. Use your graph to find the value for the half-life of the radioactive source. Draw lines on your graph to show how you arrive at your answer. Again, what we're doing here, as a different colour, that's our original count rate, 80. To work out the half-life, we use a graph to find out how long it takes to drop to 40. If we use a ruler and we go across from 40, and we look to see where it meets that graph. There we go. I'll just put a little mark there. And then if we come down from that mark there, mark it off on the axis. You can see that's 16. Again, you might have drawn your graph slightly differently to mine, so we'd allow anywhere between 15 and 17 hours. I'm just writing the answer there. So I'm writing in 16 hours, and we allow between plus or minus 1 hour. So if you put 15, 16 or 17, you'll get the marks. But it does say draw lines on your graph, so to get that second mark, that's what I should be doing then. So I should be drawing in these extrapolation lines on the graph. My first one would be there. Cross from 40, and then we go down from 40. Okay. Finally, it hasn't got a letter there. Part E. State one industrial use of beta sources and explain whether this beta source would be suitable to use in the chosen application. The industrial use that you've learned about is monitoring the thickness of paper or aluminium using rollers. You can look back in your booklet at that. In terms of whether it would be suitable or not, well, what you're looking for is the right emitter, beta, yes, and you're looking at something with a long half-life. Now if you look at the half-life here, it's 16 hours. You want something with a longer half-life than that. You don't be changing the source on a regular basis. So 1 mark for stating the right use. That's monitoring and controlling the thickness of aluminium or another material. For the second mark, you need to say no, it's not suitable because the half-life is too short. Turning on to page 66, you can see that's something you do yourself. Question 7. And that's a teacher assessed question. And that brings us to the end of this booklet. And see you in the next booklet on stars. Bye.